so welcome everyone. Thank you for coming here. Uh, and so in the abstract, I wrote about what this talk will be. The idea is to look at one particular operator called the Liouville operator, Liouville differential operator. And it turns out that it's very useful for doing both forward and backward UQ, and I'll talk about what that means. It was a surprising connection when we made this, when we were starting to write the paper, and then we saw other people also looking into operator theory for UQ. So this talk will be very basic. In fact, it will be a little bit more mathy than it's supposed to be. It's 1:20 in the afternoon, and math is not a good time to be doing afternoon, you know. But unless I'm hoping you've had a very good strong coffee and you'll not sleep when we start that. But the talk will be, the first part will be talking about this operator. We'll try to develop a very simple mathematical tool to show that it's useful to do what is called stochastic sensitivity analysis, which is the forward part of UQ. And most of this talk will take 2 hours. It's aimed at graduate students. And the next talk will be the inverse problem of that, which is used for taking samples from the posterior distribution and also for estimating the normalization constant. And surprisingly, the operator that sits to do both is the Liouville differential operator, and we'll talk about that. Okay. So what I will do is I'll give you 2 motivation slides. So I am in the lab. So whenever we come up with new methods, we have to sell the idea to, to our bosses, who will then sell the idea to their bosses, who will then sell the idea to politicians, right? And so politicians basically like the ideas to be told to them in a minute, right? And so you have to oversell their ideas. This is going to solve what you're looking for, is how you will sell it, right? So the 2 examples that I'll give basically was meant as an elevator pitch that we call. Okay, so the first example is this. It comes from coupled physics. So what you are trying to model is velocities in the ocean, let us say, and you have a particle that's floating around in the velocity field. Okay, so you are predicting if this is a particle at time t, whatever t equals to t naught. At certain time, it'll end up somewhere. Okay, that's what you're predicting. So why is it a coupled physics model? Well, you have one physics equation that works for solving the velocity fields in the fluid flow. This is your shallow water equation, let us say. And you have another equation, which is the transport equation, that is telling you how a contaminant will transport. Okay? And the idea is to take some initial snapshot of this and predict it at later times. And why is this a very useful problem for uncertainty quantification is that if you have a little bit uncertainty in where this particle is, it could either land up there at time t at some later time or there at some later time. Okay? So small uncertainty in the initial condition can lead to vast uncertainty as time evolves. And this is due to coupling effects. So there is coupling effects from one model that affects this. Okay, so where was this problem? So this problem initially was when I was in the Odin Institute with Clint. Apparently, some huge company, I think we can name companies, BP had done something wrong, right? It spilled some oil in the ocean, right? And they wanted to know where that oil spill will move because there was hurricane season that was coming. And they wanted to take care of it before media found out. So they wanted the Odin Institute people to model this for them, basically telling us if we give the full information about where the oil spill is using some satellite imagery, can you run your shallow water code and tell us where this will be at a later time? I think I was too of not important enough to be inside those meetings, but when the meeting ended, I found out that they were not going with whatever we had proposed. Because probably they didn't like the answer. But the idea is uncertainty quantification in coupled physics is a very huge thing. And in order to talk about how coupling affects uncertainty, we have to understand what it means for uncertainty to propagate in system. Okay? And of course, as usual, the higher up officials don't like uncertainty. You have to precisely tell them what will happen. They don't like probabilities, okay? What is the probability that the particle is there? No. What happens if the particle is there is what they need. So that's an additional challenge between people who are mathematicians and engineers and people who want the answers. Okay, here is another example, and this comes from where I currently work. So that was from when I was a grad student. This is from where I currently work. You know, I am from Los Alamos. Something happened in the 1950s, 40s, I guess. We did something, you know, something huge. And we took some of the waste materials, dumped it somewhere, you know. I don't want to say anything other than that because I think it's being filmed. But what I will say is something spilled, and whatever spilled went into the groundwater flow, okay? Now, groundwater physics is very complicated. So you have fluid flow through porous medium. You have rock structures that you have to account for. And you don't know when and how much spillage happened precisely, because nobody will tell you that, okay? And now what is happening is once it's in the groundwater, it will flow through the groundwater. If it comes up, it will come up through some seepage and some reactions. It'll even come up to your groundwater well, okay? And the problem is we want to quantify this. So what happens if there is real climate change, this rain starts falling in? That's a different initial condition. Where will the contaminant plume end up in like 20 years from now, provided that you know where it is right now, okay? And this is a very hard problem. In fact, we've been trying to do this, but there's very limited data. There's only been one well that has been monitoring contaminants since the 1950s, so you have sparse data. So this is the regime where we say that we are important, and in the sense that by we, I mean people who do computational science and engineering. Because we bring in the models, we cannot rely only on data. So the question is, how do you take your model, how do you take this limited data and answer the question that people want to answer? What happens when we have change in initial condition due to climate change? Okay? Can we reliably predict where this contaminant plume will end up? Because if we cannot do remediation acts. Okay? All right, so these are the motivations. This is what I wrote in the proposal. Say we will answer this question using operator theory, okay? And the idea is we haven't answered this question, of course, but if we answer it, we won't get the money. So you get the proposal, you get the funding, you work on it, and then after 3 years you say, hey, we couldn't answer it, but we did something else. Please give us money so that we can do it in the next 3 years. And that's the trick. Never solve the problem in 3 years. Okay, so there are these basic questions that we need to answer. What governs the propagation of uncertainty in dynamical system? This is a very vague question, okay? What do we mean by uncertainty and what do we mean by dynamical systems? Okay, so the dynamical systems part is the easiest thing. That means that you have a model that gives you the state evolution in time. Okay, what is state, what is model, we'll come back. But what is uncertainty? Okay. And this is, apparently this is very controversial, and this is somehow seems more philosophical than mathematical. When I started doing UQ, I had just finished my graduate degree in numerical analysis. Nothing was uncertain for my thesis. Everything was certain. You know, I knew the initial condition. This was the model. I have to solve it. And if it matches data, so be it. If it doesn't, well, the data is wrong, right? But when I started doing UQ, our problems were different. We had so much uncertainty. I mean, what if the model is wrong? What do we know about the parameters? What are we observing from the model? What data do we have? And so all of this was kind of different from how statisticians view uncertainty quantification. Okay, so therefore this became part of computational science and engineering, which is what we call UQ. If you go to a stats department, I think now they are thinking of UQ coming from computational science and engineering as a valid question, but before the statistician answer was very different. So how do we actually solve this? And there we got into the same fights that statistician had before, 50 years before, which was the frequentist versus Bayesian. Okay. And there was this whole thing like, what does it mean to have probability distribution for a parameter? You know, a parameter is not random. What is it? What is random? You know, you're solving a deterministic system, so how can it be random? All this very useless discussions that led to what does it mean for an uncertainty to propagate. So unfortunately, I don't have an answer. Okay. So all I know is if there are things in your system that you want to model, the way you describe probability or uncertainty is by describing a probability. Okay. And that is it. It could either be a PDF, it could either be an estimator of some statistical quantity, but if there is probabilities involved in your system, that is the way you do uncertainty modeling. Now, what does it mean for uncertainty to propagate? Now, this is something that is surprisingly still not fully understood in my mind. And what I think what it means is if you have a state, if you have a dynamical system, if you have an uncertainty in the state, then when the dynamical system evolves, that uncertainty changes over time. Okay? So this is what I mean by uncertainty propagation. But this is, as I will tell you, there are some technical issues with what that means when you have models in your parameters. Okay. And so these two questions, this first question, while very controversial in terms of philosophy, it's kind of easy to describe in terms of mathematics. This, on the other hand, I was surprised that there was no answers for it when we were looking for it. So how sensitive are quantities of interest to model parameters when you have uncertainty? I thought this, somebody must have solved this 50 years ago. But apparently no one had done this in a framework that we thought was useful. And the third question is, well, if you have coupling now between different physics, you have uncertainty from one physics, you have uncertainty from one physics. When you couple models, where you have multi-physics modeling, how does your uncertainty quantification take place? I don't know the answer to that one. So this talk, and mostly the research that I've been doing, is kind of attempting to answer 1 and 2. I still don't know what 3 is, okay? All right, so here I think I would have written a little bit, but I'll wait for it later on. I think I'll start the board a little later. Okay, so why operator theory? This is kind of the new thing here, okay? You may have or may not have seen operator theory. Last 6 years it became huge in the community. Koopman theory, dynamic mode decomposition, they're huge now. They are attempting to solve problems that are sometimes novel, but sometimes they don't have the right answers. But they are what is called operator theoretic view of looking at your system. Okay, so briefly I'll describe this. Look at the top row. And so let's say you are solving a PDE, okay? Your PDE is a differential operator. It acts on functions, but you discretize it so you can think of it acting on some finite dimensional vector, right? The space of your discretization. So your actual model is a differential operator. When you discretize it, it works on finite dimensional, and it's typically nonlinear. It's mostly you solve nonlinear PDEs. In real life, you never solve linear PDEs, right? Okay. Now these two operators, they don't act on the state, but they act on functions of the state. So that's a different viewpoint. Now, what have we done? Well, when we discretized it, our state was finite dimensional, but the set of all functions on that finite dimensional space is infinite dimensional, right? So now we are working on infinite dimensional spaces. But the good thing we get is it's linear. Those operators are linear, okay? So we trade finite dimensional for infinite dimensional, but we remove the nonlinearity and get linearity, okay? Now, why is linear important? Almost everything that we do, everything that we can prove is for linear. So nonlinear, I mean, you do hodgepodge techniques. You do it for one thing, you do it for other. But a general theory, very nice theory that a mathematician would be proud of and will go to sleep nicely at night is if their things are linear. Okay. So the Koopman that became really popular was about state reconstruction or surrogate modeling. So the idea is if you have snapshots of your state, can you learn this linear operator that acts on functions of those state? And if you learn that, you can actually build a surrogate for your state. So this was very bizarre. I mean, your state is this high finite dimensional object by choosing 10 or 15 functions, and I told you, remember, this is infinite dimensional, but by choosing 10 or 15 functions of your state, you can reconstruct the state. So that was what Koopman, DMD people did. Of course, it works when you have something, your PDE is doing something vaguely linear, not fully chaotic. They were also showing it for like flow over a cylinder, where you have these very periodic phenomena, and you can reconstruct that state using this Koopman operator, or an approximation of this Koopman operator. Okay? So the Perron-Frobenius, on the other hand, also acts on functions of state. Okay? And this is what I will focus on. So instead of just pure valued functions of your state, it works on different functions, probability densities on the state. So a probability density is also a function, right? It's a PDF, it's a function on the state space. And it tells you how those probability densities evolve over time. Again, it's infinite dimensional. So the idea is, can we learn a Perron-Frobenius operator? And if we can learn, then we know how uncertainties evolve on the state, okay? So this is operator theory. What does it do? So operator theory in a nutshell. Well, I imagine you've all taken this linear algebra courses, right? So how far did you go with your linear algebra course in undergrad? You probably have done spectral decomposition, some sort of decomposition theorems, polar decomposition, right? All that, norm estimation. Those work on finite dimensional spaces, okay? Now, if you have infinite dimensional spaces, you can still do those things. And that is what operator theory is. You can still get the spectrum of your operator. What it means is another matter altogether. You can still do an eigenvalue decomposition. You can still do the polar decomposition, provided you have linear transformation between function spaces. So for example, all the differential operators are infinite dimensional, right? Truly they act on spaces of functions. Okay, so this is a very old theory actually. If you look at Koopman theory, that was in the 1950s. Operator theory actually came about when von Neumann said, hey, I can make everything linear algebra. And that was a genius idea when he was looking at matrices. He said, okay, what if I have infinite dimensional? I can do the same thing. I can move adjoints and it will work. And I can do a spectral theorem and it will work. And so once von Neumann said it, you know, we got this fancy operator theory technique in math through physics. Koopman was in the same idea in the 1950s. So all this theory is from the 1950s and it's starting to get used now. That's the amazing thing about math, that you know somebody does the theory in 50s, 60s, coming from very different motivation, and it finds usefulness in this world. Okay, so what will my talk be about? So my talk will be about, especially if your model is an ODE. Very simple to understand, okay? I know, so you all are experienced with a PDE-based model. So for example, you're solving Navier-Stokes shallow water equation. That's a PDE-based model. When you discretize it, you do get an ODE, right? So for now, just think of your model as an ODE. It's describing something. It's given by an ODE. And this is the ODE, dx by dt equals to f of t x theta. And theta are your parameters of your ODE, okay? X is the state. So an ODE acts on finite dimensional vectors. A PDE acts on functions, okay? All right, so all we will care about is the dynamical system. And we will think of this in terms of operator theory. So what do I mean? So when I give you a model, you immediately think, okay, if I start with an initial condition, I solve this ODE, then I will evolve my state to the next time. I can do this through some time integration. That is the image that you have, right? And again, if it's a PDE, then you will discretize the space, right? You will get your function approximation on that space, and then you will evolve the PDE from time t equals to 0 to t equals to 1. Operator theory doesn't look at it in that way. Operator theory looks directly at this operator that is acting on the function, or on the vector x in this case, okay? So what does it mean? So here is what it means. I think I'm going a little faster than I'm supposed to, but I'll slow down, okay? As soon as I'm coming towards the end of my talk, I'll kind of slow down the pace so as to fill out the time. Okay, so what does it mean? So again, you are now working on an ODE, and look at this middle row. It tells you that if you start a state at time t, to go to state t plus 1, you solve the ODE. You move, you do some time integration, you move from t to t plus 1. Okay? If you look at any function of your state, a scalar valued function of your state, then that moves from t to t plus 1 according to this Koopman operator. And if you look at the PDF at state t, and you put it over there, the PDF moves from t to t plus 1 by the Perron-Frobenius operator. So if at time t, the state is given by some multivariate Gaussian, then at t plus 1, it will have some distribution, and that distribution will be given by the Perron-Frobenius operator. So it is mapping distributions. Whereas your ODE is mapping states, and your Koopman operator is mapping observables or scalar valued functions. All right. And the whole idea is, can we learn this Koopman operator or Perron-Frobenius operator? If you are actually solving a PDE, you do have to learn them. But if this is an ODE, this is given exactly by an operator. And I'll tell you what that is. Okay. In a minute, though, not right now. Okay. All right. So this was my elevator pitch to folks at Lano. I said, hey, you have coupled models, right? You have two physics models that are interacting. You're solving a multi-physics problem. Your model 1 and model 2 are coupled. You have uncertainty in model 1. You have uncertainty in model 2. Somehow they're going to get combined, and that's what you want to understand. Okay, so here is what you do. You take this coupled system and learn the Perron-Frobenius operator from it. Once you learn the Perron-Frobenius operator, now when you predict, you're doing probabilistic predictions instead of point predictions. Okay, what is the inverse problem? You have some data from your model. Let's say there's a satellite observation that's observing data from the model. You use the data and you use the Koopman operator to kind of data assimilate back into the system and tell you what the real densities should look like posterior. So the idea is, if you have a prior, push it through the Perron-Frobenius, get predictions. If you have data, pull it back through Koopman operator and do a posterior. Okay? So they act in this forward and backward thing. So this is what I mean by forward and backward UQ is your forward UQ problem is just pushing the prior distribution through your model to do predictions. And you're not only giving your point predictions, but you have to give probabilistic predictions. So if you have a prior, you are interested in what is the probability my state is going to lie in this region. Okay, what is the expected value? What are the moments that I can observe? And when you have real data, you use that to kind of tell you, okay, this is not what my prior should be, this is something else. All right? Okay. Oh, so I'll kind of, this kind of sets up what I'm going to do now. So before I start into the heavy math, trying to derive things here, I'll just briefly tell you about the papers and publications that we have done using this method, and kind of introduce you to basic ideas about forward and backward UQ and what people are doing these days, okay? Because apparently the landscape of UQ has changed. In 2014, it was fairly simple, very easy to understand. In 2024, I don't know what is UQ anymore. So there is something called UQ, and apparently whatever you do is UQ, okay? So something has changed. All right. So briefly, I'll talk about these 5 papers here because they give you different ideas about what the UQ problem is. Especially this paper will be my second talk. That's the inverse problem to the forward problem that I'm talking to you about. Okay, so the first is we did what is called semi-supervised learning, and I'll give you an example of what it was. So there is the Mars rover that is roaming on Mars, right? It's throwing lasers on rock, and it's trying to figure out if there's life on Mars, all right? Okay, so when it throws lasers to rocks of Mars, depending on the composition of the rock, when the laser hits back to the Mars rover, there's some change in frequencies, right? And it's going to analyze that and tell you what specific components are in the rock, and it's looking for carbon, okay? Carbon forms. All right, the problem is all it can do is it can throw lasers and collect lasers. There has been no real analysis of data done on Mars. This is the only thing that the rover can do. On Earth, in fact, we have shot lasers on rocks. We have learned from the reflected lasers what chemical compositions are there. We have learned that mapping. So based on the spectroscopic data, I can tell you that, okay, there are these 4 or 5 metal elements or composition in the rock, okay? I don't know that on Mars because I haven't done the study. So the idea is, can we use Earth data to kind of infer something from the Mars data? And if the Earth data and Mars data look really the same, that means they must have similar things in the rocks. But if there is some difference, then that is what we should be looking for. Okay, so how do you do this? So the way people predict what is in a rock is through some standard statistical techniques. So they look at the spectroscopic data, and they have done tests. So if there is carbon in there, this is what it should look like. If there's silicon in there, this is what it should look like. And so when they get the real thing, they can then do a regression analysis and tell you what all there are, okay? So we have done that on Earth. So we wanted to apply the same model on Mars data, but we don't have that information. So the idea was you look at the probability distribution of spectroscopy on Mars and compare it to spectroscopy on Earth, and try to learn what probabilistic differences are there between them. If you can learn that mapping, then you can take that probability distribution on Mars, map it to probability distribution on Earth, do your statistical analysis technique because they are from the same distribution, and then infer, right? And this way you can also do something like outlier detection and say like, oh, there is not enough, there is this huge difference between what Mars is and there's Earth. So apparently we found real spikes on some of the data set. The whole idea was using normalizing flow to do how probability distribution can be mapped, and I will talk about normalizing flows in a bit. So this was the first paper. The UQ is just based on statistical models and data. There's no computational science and engineering here. Apparently this is a very math paper, but what I found very amusing was when people do machine learning, they take derivatives, right? So you take derivatives, you do backpropagation. When your input is a symmetric matrix, you do backpropagation, you get errors. And that's because some guy wrote the wrong derivative with respect to symmetric matrix. So we kind of corrected this, and we said, hey, like if you really want to do backpropagation where your input is a symmetric matrix, you need to correct your algorithm because that's not the derivative with respect to a symmetric matrix. This paper is exactly the talk that I'm giving now, but based on a simpler idea and more math, okay? This paper is the inverse problem. And I don't know how many of you are knowledgeable of Bayesian methods and sampling, but I will talk about it when we get there. And the idea is it's the inverse problem to this problem. Right? Okay. And the last paper is about data assimilation. The slide that I told you about, if you have data, you want to understand from the data and inform your priors. Okay. So I won't do any data assimilation here, but it's good to know what that data assimilation problem is. Okay. And we did some presentation, and I don't want to talk about here. All right. So let's see. So I do have. So unfortunately, there is a code base which is not open. So if you want to use it, you cannot yet. We will get it approved, hopefully. With the lab, it takes time. But once we get it approved, I think this method does adjoint sensitivity and stuff like that I'm talking to you about. So if you have a forward model, all you have to give is the prior information. And it will find out, and quantities of interest that you want, and it will find out how sensitive those quantities of interest are to the parameters, either in your model or in the initial condition, okay? But the model has to be in ODE, so you have to give it as a discretize. If you have a PDE, discretize it and give it to us, or if it's an ODE, just give us the F function. That's all we need. Okay, so here is the theory, and before we start, let's take just a 5-minute break, and get a paper and pen ready if you want to. Yes.
Can it also handle DAEs?
Yes, so very good that you asked. So our next proposal is extending this to DAEs. So apparently there is no operator theory for DAEs. So we are trying to find out what is the direct analog of a Perron-Frobenius operator when you have a DAE. Yeah, that's a very good question. Unfortunately, we don't know the answer, and it's a good thing that we don't know the answer. So if you publish anything, even though it's crappy, you know, it's going to get attention. Okay. So yeah, I'll start this in 5 minutes. So what time is this? 1:50. So 1:55. And yeah, and that way, you know, so we're going to get hit with math. We're going to understand what it means for us to take derivatives, uh, but in the operator theoretic sense. So yeah.
It's muted now. You cannot visibly see it, but I can.
Okay.
Oh, now it's unmuted again.
Oh. All right, so get ready to sleep, okay? Oh, so as I said, our basic model is an ODE. That's the simplest to understand. Um, Not only is it simpler to understand, but all the operators that I talked to you about, the Koopman and the Prof, they have closed form. So that means we can analyze this to death, we can derive our adjoints, and then we can actually give you the results of sensitivity. When it is actually in PDE, what do you do? So far, we don't know the answer. The immediate thing is take the whole ODE, PDE, discretize it, you get a PDE, but that is a ODE in very high dimensions. So the second best thing to do is do some surrogate modeling. So you don't want to do an estimation for the entire state. You have certain points that you care about in your simulation. You learn a surrogate for those points based on your ODE simulation. And most surrogates can be casted as an ODE problem. Okay, so even if you do Galerkin projection and stuff like that, or reduced order model using Koopman and DMD, you can turn your original PDE into an ODE with respect to certain things. Okay. Of course, in Koopman, the X will be the Koopman modes. So that's why we won't worry about where this is coming from. In order for you to understand what an operator theory is and how is it applied, it's better to keep it as an ODE. Okay? And here were the questions that we asked. So what governs the propagation of uncertainty in dynamical systems? And here, you know, I'll tell you a surprising thing that I think a lot of practitioners, even in Bayesian community, get something missing here when they use the additive model, additive noise model. And I'll talk to you what that means. So even if you have an ODE, there is a stochastic process underlying it. And the second question was, how sensitive are quantities of interest to model parameters? Okay, and we will go through this with simple examples, basic derivations, and figure this out. Okay, there is uncertainty in initial state. There is uncertainty in model parameters. Okay, and if we want, we can include state and model parameters as a state object. We can augment it. So we can take x and theta, put it in a vector, and call that our state. And now we have an ODE in that, where dx by dt is this thing, d theta by dt is 0. Okay? So you can augment your model parameters and initial state. Of course, it's very, very, if you have large model parameters compared to state, then you have increased the dimension of your problem. And where will you have more model parameters than you have state? For example, if F is a neural network. Okay? So if F is a neural network, the parameters of the neural network are huge. Even if you have 3 layers of neural network with a feed forward, you will have a lot of parameters. Okay. All right. Okay, so what is a dynamical system? Let's take this viewpoint from discrete dynamical system. Okay, even though that is continuous, it's better to see them as something discrete, which means that there is a mapping like this going on. So you have at t equals to 0, you have your initial state space. At t equals to some delta t, you have your state space at that time, and then the next time. Okay. By h, I mean some observable of your state. So some scalar function of thing that you can observe. Okay. So typically when you have system, you observe something from the state. It has to be some function of the state that you observe. Now there are things that you don't observe. You don't observe the initial state. Okay. You don't observe the model parameters. Typically they are unobservable. Okay. All right. There's something that okay. Let's look at an example. So for example, the 3-dimensional Lorentz equation, is everyone familiar with Lorentz here? Okay, this looks like this butterfly pattern. So it's an ODE in 3-dimensional state space, x, y, and z. So the x times 3 looks like this, the y looks like this, and the z looks like this. Okay? It has 3 parameters, sigma, beta, and gamma, that I have not written here. And maybe the observable is the norm of the vector at each time. Maybe that's what you're observing, or maybe you're observing just x, or just y, or just z. Okay? So a dynamical system is this. It's a mapping from the state space along with an observable. Okay? Typically, the observable part is not important because mathematicians don't care about observables, but physicists and when we do UQ, we care about what is an observable. All right? Okay. Now, there's one more thing going on that I haven't put here because I'm not doing inversion, but the data that you have is a noisy version of the observable. Okay, so if you do some noise here, that's the real data that you get. All right? Okay. Okay, so what is a stochastic process? So remember, I said we're talking about dynamical systems from operator theory, and we want to do UQ. All right? So if we want to do UQ, we have to talk about probabilities. So what it means is that you have a probability measure at time t equals to 0, you have a probability measure at time t equals to 1. If you give me the whole set of probability measures, that is a stochastic process. Okay? So again, in this scenario, I don't like the author, but this comic illustrates what a stochastic process is. So even if you get a sequence of 99999, you can never be sure if it's random or not, right? So just looking at trajectories of a stochastic process doesn't tell you if it's a stochastic or not. What you need to do is you have to account for probability measures. Okay, so in your dynamical system, this means that if I ascribe a probability measure at t equals to 0 on the state, and at every point in the state, then I've described my stochastic process. Okay? Now, I don't have to, if I do the state thing, I don't have to describe a probability measure on H because it induces it. So if there is a probability measure on the state, H will be just the push forward. All right? Okay, so this is a stochastic process. So if you give this to me, I have completely described the system probabilistically. The question is, you cannot give this to me, right? This is a difficult problem. The only thing that you can give me is, if you didn't observe the state, you can put a probability measure on the state at time t equals to 0. If you didn't observe the theta, you can put a probability measure on the model, and that's the only thing that you can tell me. I have to come up with the probability measure each time based on that information. So that is the forward problem. The forward problem for an ODE is, given a probability measure at time t equals to 0 on the state, given some information about what the measure is, I will tell you how the probability measures propagate in time. That is the forward problem. What is the inverse problem? So can someone tell me, or even if you, this is just so that I wake you up, okay? I'm not going to deduct points from you. I don't have that capability. but if the forward problem is giving this probability measure, and forget about the theta for now. If I give you this probability measure, your job is to come up with all the probabilities. What is the inverse problem?
You come up with theta when you know the data.
Yeah.
What theta is.
Yeah. So given the data on the observable, your job is to come up with that probability measure t0. Okay. And yeah, theta also, if theta is there, but for now, make it even simple. Take away the theta. So there's no model parameter. The only thing that you don't know is the initial state. And if you have some data at later times, your inverse problem is to come up with that measure. Okay? Now, there are two ways to do it. The one way to do it is get samples from that measure given data. Or the other way to do it is Bayesian. You do some prior and you get a posterior from it. Okay. Now, here is the problem with any of that method is, what is incomplete is when you have data, you have to somehow complete this thing. Because you don't have that. Remember, I told you, if you have that probability measure, then you know what the probability measure of the observable is. But if you don't know that, all you have is data, you have to come up with a model here. So whoever comes up with a model there, is your inversion problem tied to that model that you selected, or is agnostic of the model you selected? That is a thing that no one has discussed in sufficient depth. Okay, so having said that, why is this a stochastic process? So let's take a time here, like a few seconds, because yeah, there was this very important German physicist, you know, who came up with a description of stochastic process. Does anyone know who that scientist was? You know? Yeah, he's famous with this hair, crazy hair, you know? No? Well, I mean, Einstein was German, right? Okay. Uh, so here is the thing. What is a stochastic process? Okay, where can I use this board? Can I use this? Okay. All right. Okay, so here is what is a stochastic process. So remember I told you what is an ODE. So if you start with an initial state, if I tell you x dot equals to f of, then I can solve this ODE and get a trajectory. Okay? This is x naught. Okay? You can evolve the initial condition through the ODE and get a trajectory. All right? There is also the reverse. If I give you a smooth trajectory, you can pull back and say, oh, it must have come from this ODE. Okay, so they're kind of twin to each other. Now, here is what Einstein discovered when he was looking at molecule, things moving in a molecule. Or the best way to describe it is if there is a dust particle that is moving in some gaseous room. Okay, so he observed this. And the question immediately to answer was, is that coming from an ODE? Right, and the answer is surprisingly no. So this roughness in the path is what leads to a stochastic version. And the real tricky and the real genius of that paper was, well, all you need to do is think of this as an average of so many samples that are happening. And all I care about is if I am at time t, if I want to go to t plus 1, I can go here, I can go there, I can go here, I can go there, I can go here, right? There is some probability that tells me where to go, and this that I've observed is kind of an average of all of those things. And so that was a genius thing. So that led to, of course, the stochastic ODEs, but the idea was if you look at real trajectories, they do not correspond to ODEs at all, okay? Now, I told you that the ODE in the probabilistic picture is also a stochastic process. So and I told you this is coming from a stochastic ODE and this is coming from a deterministic ODE. So why is that a stochastic process also? This should not be a stochastic process. And here is a trick. If I give you x naught, yes, it's a trajectory here. But if I tell you that x naught is coming from some probability distribution, which means that my x naught could be anything. Then if I evolve this, I will get a smooth thing here. If I look at a certain time t here, there is a probability density. Right? So at a certain time, if my initial state is unknown, I do get a probability density. But the crucial thing here is that this probability density doesn't depend on t minus 1. All it depends is this initial PDF that you gave me. So, okay. So it is a stochastic process, but a very degenerate stochastic process where xt given on xt minus 1 and everything prior to it is just xt given on x naught. Okay? On the other hand, this one I told you is dependent on xt minus 1, exactly. So there is stochasticity when I'm time t to go from t to t plus 1 in that one, but here it's not. Okay? So if I know in fact t minus 1, I know t directly. So that is, oh, this is not supposed to be this. Sorry. It's been a while since I was teaching. One should work, right? That one?
Yes, we need to use the liquid.
Ah, okay, okay. I see.
This one, yes.
That one, okay.
Yes.
That's
wait,
good.
let me just wait here.
Sorry, folks.
No, it should be.
Is it okay to leave it for the next lecture? No, no, I'm just kidding. Yeah, okay. Yeah. So let me get back to the. Oh. All right. So now, does everyone have any questions about what the forward problem is? No, right? Okay. So we have a deterministic ODE, but we still have a stochastic process because the initial state that we have given has an uncertainty that is given by a PDF. Our job is to compute PT1, PT2 through PTN. Okay, if we have done that, the forward problem is done, at least in terms of probabilistic prediction, not yet in terms of sensitivity. Okay, so the answer came from Liouville's theorem. And Liouville's theorem tells you that, okay, if you give me the initial uncertainty as a PDF and it's smooth, all we require is some sort of smoothness, then all other probability at any time is given by the solution of a PDE. Okay? So yeah, so take your time in trying to understand what this means. So you have your ODE, which is dx by dt equals to f. Your initial condition has a probability density. And Liouville's theorem is telling you that if you want the probability density at any later time, all you have to do is solve this PDE. Okay? What is the catch here? This is an ODE in some state space. Usually ODEs are 3, 4, 5, 10, 15 dimensional, 20 dimensional. This is a PDE in that much dimensions, right? So we are only used to solving PDEs in 2 and 3 dimensions. This is a PDE in the dimension of the state space. How do we solve it? In fact, we cannot solve it. Although recent advances in AI are doing that, they're solving these very high dimensional PDEs, and their examples comes from stock market. So apparently in stock market, if you want to gamble somebody else's money, you throw this PDE and it tells you when to bet. And that PDE comes from an equation whose name I've forgotten. I'll remember it, but it's a high dimensional PDE. So people in the financial world wanted to solve that PDE, and for a long time they couldn't. And then suddenly AI became huge, and AI is now used to solve PDEs. You must have heard of PINs, a physics-informed neural network. They aren't as great as our standard computational science methods, but the good thing is they can solve PDEs in any dimension theoretically, right? You don't need to be tied to discretization of your space in 3 dimensions. Okay, so Liouville's theorem was for a long time just this, a theorem, because you cannot practically solve it. But as I said, we are in the world of AI now. So AI should be able to do something that people couldn't do 100 years ago. Okay. So what we are saying is that we can be less smarter and just throw in AI, right? Instead of being more smart and trying to figure out a way to solve a general problem. Okay, so what is operator theoretic view of the propagation of uncertainty? Now the theoretical view is a little bit complete. Your original dynamical system tells you how state evolves from t to t plus 1. In terms of operator, it's this operator. It acts on state. Okay? This is an ODE operator. Well, the densities, remember, they are functions of your state. They act according to the Perron-Frobenius operator, and that operator is this operator. So your original operator acts on state. Your Perron-Frobenius operator is a differential operator also. It acts on PDFs. Okay? So by the way, okay, how many of you have taken a basic fluid mechanics course or any computational mechanics course? Okay? 2, only 2. Okay. Can you tell me what that PDE looks like? Yeah. It's a mass conservation equation. So the transformation operator is just a mass conservation equation, which makes sense, right, for probability density. If your ODE is evolving states, nothing wonky is going on. So whatever initial mass you have has to be conserved. It's just that the shape will change based on the dynamics. Okay. So apparently all our answers were just solving the mass equation in high dimensions. All right. Okay. Now let's come up. This is the part of the graduate thing. Like I'll ask you to solve something. I'm just kidding, but we'll see. Okay. So if I tell you dx by dt is equals to f of t x theta, and I tell you that the ODE is linear, right? So for now, forget there is any theta. Just a dot x. A is a metric, is a matrix. X is a vector, and I tell you my initial density is the standard Gaussian, two-dimensional standard Gaussian. Okay? Can you tell me what the probability density will be at any later time? Just with this information. If you cannot, it's okay. I'm just kidding. It depends on A, yes. It definitely depends on A. But there is something special when it is just linear. So it's going to be normal. It's just that the mean and the covariance will change. Yeah. And that will depend on A. But a normal transformation will remain normal. This is the direct analog of when you have a density and you do linear transformation, and you have a Gaussian, you will remain a Gaussian when you do linear transformation. This is the continuous analog of this. So in fact, you can derive this. We know that it will be a multivariate Gaussian. Oh, oops. No? Okay, I have nothing here. All right. So we know this will be a multivariate Gaussian. And the way to derive this, if you know about ODEs, you know that this is e to the power at times x, right? Where e to the power at is the matrix exponential. That is the sum of matrices, because every matrix you can do a Jordan decomposition, okay? And when it's very simple linear transformation, you can find that matrix exactly. And because it's a linear transformation from initial condition to any time t, your probability density will always be Gaussian. Okay? All right, so this is what we plot here. So you start with the Gaussian. If I take that one, a simple standard Gaussian becomes this stretched Gaussian as time evolves. Okay, so that is what it is happening. And here is the thing. This is actually AI learned. I haven't plotted the exact one. So this is what AI learned, and I'll tell you how we used AI to learn the probability density. But what is happening is a very standard Gaussian is becoming this tilted Gaussian because of this linear transformation. Okay? And so you can derive what the probability density will be at each time. This is given by this thing. Then this is a quadratic form, so this is a Gaussian distribution. Okay, so now here is the question that I want to ask. You have classically solved the forward UQ problem, because you have now given me probability distribution at each time, for this problem at least. But you still haven't been able to solve this problem, and that is this. If I tell you what is d by d theta of these quantities, right? So there is no way, no theorem that tells you what this is. Even for that simple case, well, if it's a multivariate Gaussian, you know the moments, right? So you can figure that out in terms of theta and take the derivative. But in general, there is no theory for what this should be. So how will you do this? Let's say you did not, you forgot to come to this lecture, right? Because I'm going to give you an answer how you'll do this. But let's say everything that you've studied so far, I give you this problem. I give you a very simple ODE, I give you an initial condition, initial PDF, and I tell you, okay, find me the derivative with respect to parameters of all of these moments, okay? And what is the way you will do it? What are some of the ways that you know or you can think of that you will do this? What is the most naive way? Yeah, so finite differencing, right? So that's a good answer, but remember there is a little bit tricky here. What are we, so to compute the finite difference here, we will have to do, we'll take a small theta, right? We'll do theta plus h. We will compute this expectation 2 different times divided by that delta theta. Okay. So how will you compute the expectation 2 different times? You will do Monte Carlo. So you will draw samples from the initial condition, you will run your model at that time, and then you will compute the expectation of that function, right? The problem is Monte Carlo estimates are finicky, right? They have this variance thing. When you do derivatives with Monte Carlo estimates, you will get wildly different thetas, wildly different derivatives, just with naive Monte Carlo. So there is no wonderful way to do this without incurring some sort of estimation or difference. So there's another way which is called polynomial chaos, which tells you how the moments in a system evolve if you start with some initial condition. And then you can do the moments. But suppose I change the function. If I give you any other function instead of moments, you'll still be having the same problem. Right? If instead of moments I tell you, hey, what is d by d theta, that the probability that the state lies in some fine tail, how will you compute that, right? So the forward problem, as we thought before, is still incomplete in this scenario because we cannot compute sensitivities with respect to model parameters. Okay. And here is a general problem. Take any quantity of interest which I write as expectation with respect to the time varying probability density. What is dq by dsi? And g now could be anything. It could be a probability, it could be a moment. Si is any parameter. Okay. All right. And the problem with finite difference is, once more, if I have more thetas, if theta is in a very high dimensional space, imagine taking finite difference in that high dimensional space, right? How will you do that? Okay. So finite differences of Monte Carlo estimates are tricky. Theta is in high dimensional. How do we do it? What is the general theory that tells you what this should be? Okay. All right. So this is what we'll give you. I'll give you one other example so you know what I'm talking about. Let's start with Lorentz equation. For a given initial condition that starts at 0, 0, 0, this is the trajectory, right? If I now tell you the initial condition is coming from a PDF and I'm interested in this quantity, what is the probability that my Lorentz state is within a rectangle at certain time, right? Now find out dq by d sigma, let us say. And how will you do that? So this is slightly tricky with Monte Carlo. So how will you do this with Monte Carlo? You will take a bunch of initial conditions, run this for each time, check if it is within a rectangle or not, right? Then divide by the number of samples. That gives you the probability that is in a rectangle. That is for a single parameter sigma. You do a sigma, sigma plus h, do the finite difference, and you will get the thing. I bet you if you try to do this, you will get widely different answers because this is a very chaotic system, even with respect to parameters, right? So you will get crazy answers for the derivatives if you do Monte Carlo estimates. So in order to get very, very good estimates with Monte Carlo naively, you have to take so many samples that it's not even worthwhile. Okay, more than 1,000 for the three-dimensional case. All right, so here is the answer, and should we stop at 2:30 and then continue, or because we will get into proving this theorem, so. So the answer is this theorem. The derivative with respect to any quantity of interest with respect to parameter is given by this integral, where I'll tell you what V is, but the only problem is you need to know what the time varying probability density is, right? So with Monte Carlo, you didn't have to know that because you just evolve the samples. But if you really want the answer, you need to know this time varying probability density, okay? Which kind of nullifies the method. If I can find the time varying probability density, then I can solve anything. But I'll tell you how this can be turned into a learning algorithm. But this is the exact answer. Instead of finite difference, which is an approximate answer, this is the exact derivative of the quantity of interest with respect to a parameter. The only thing is, how do we estimate this? Okay? And what the hell is this V? Okay, are we allowed to say, okay, sorry, what the H is this V here? Okay, what is the V? And that is coming from the adjoints. So I'll tell you what is an adjoint, but maybe let's take, I don't know, 15 minutes break or 20 minutes break. So this is, as I said, this is the exact derivative. It depends on solving this integral. And this is nice because there was no exact representation of what it means to take derivatives of quantity of interest with respect to parameters. So what I mean by exact is it doesn't depend on what f you take, it doesn't depend on what probability distribution you have initially. There's no dependence on any model. This is arbitrarily, give me a function, give me an ODE, give me an initial condition, I will figure out the density, the derivative estimate, okay? And the beauty comes from figuring out adjoints. So what is adjoint? And before I go there, I'll tell you what this V is. If you remember what this L operator was, the L operator was the Liouville differential operator, right? Which was the mass conservation equation. Its adjoint is that operator on top. And the V that you saw is the solution of this adjoint PDE. Now, if you remember the picture between Perron-Frobenius state and Koopman, this adjoint is actually the Koopman operator. So it's how neatly it ties out. So when you have a state, the probabilities evolve according to the Perron-Frobenius operator, but sensitivities evolve according to the Koopman operator. Which, I mean, I was very happy when we discovered it, so much so that I decided that we won't have any result. The math is nice. But I think my co-authors told me, like, let's have some results, you know. The paper is better if we have some results. Okay, so I'll talk to you about what an adjoint is. Why is this important? And this ugly looking equation is actually very easy to solve in 1 second. So that is what I will show, provided you know a little bit about what a hyperbolic PDE is and all that stuff. Okay? All right, so what is adjoint? So what do all of these quantities mean? Remember, this is the exact derivative. Let's look at an example and see what these quantities mean, okay? So that you know before we prove it. So again, that is the equation on top. Let's take our simple linear dynamical system for now, okay? You have a standard Gaussian. I think there's a square missing there. Okay, so our parameter of interest, there's only one parameter now, theta. So all we want is derivative with respect to theta, okay? And our quantity of interest, let's say, is just the expectation, the first coordinate, okay? So that is the quantity of interest. What is dq by d theta? Okay. All right, and according to that theorem, we have to compute a partial derivative of f with respect to theta and the derivative of initial condition with respect to theta. Well, that is easy. There's no theta dependence on initial condition, so that right-hand side goes away, okay? Now, f is the dynamics that is given by this. That is just this in terms of vector language, right? So you can take the derivative with respect to theta here. Okay, that's this vector. Now, do the divergence. You can expand the divergence to be p times divergence of this, grad p times this. And so you find out that the divergence with respect to theta is just 0, right? I mean, of f of theta. So all that remains is this term in there that you have to solve for, okay? Provided you know how to do the adjoint V. And now we'll come to the adjoint, okay? All right, so the adjoint looks very ugly. It's that operator, d by dt of grad V, okay? And the adjoint PDE is L of V equals to 0. So what you want to solve for, you want to find the V such that dV by dt plus grad V dot F is equal to 0, okay? So does anyone know hyperbolic equations or theory of PDEs? How many have studied PDEs here? Okay, only 1, 2, 3, okay.
Shallow flow equations are hyperbolic.
Yeah, so shallow water equations are hyperbolic. There's elliptic equations, there's parabolic equations, okay? So the cool thing about hyperbolic is the information flows from initial condition to any time through characteristics. And characteristics are these curves in space-time, okay? So for example, if you want to solve a PDE, you start with an initial condition, and you use your fancy numerical method, you get the space-time value at the next time step, right? But instead of thinking of a solution over the whole space, think of a solution just connecting the initial condition to some point in space, okay? And if you do that for every point in space, you have the solution. So characteristics tells you that if I want to go from one point in space to another point in the space at a different time, then I have to follow the characteristics. And information is only going in those directions. Okay. So here, if you actually derive the characteristics, and if I have time, it is 1 minute to derive it, and I may just do that. The characteristics are constant, which means that whatever the characteristics is at time t equals to 0, they will be the characteristic information at any time t. So all I have to do is look at the initial condition on this. I know that v of xt is g of x. Because characteristics are constant, this will be the value at any time t. So how do I get that? I take an initial value, I evolve my ODE to time t star, I look at the value of g of x, and that value should be exactly the value of my initial condition of that thing. Okay? Now, what I told you about adjoints flow information backward in time. So your initial condition is at t star, and you're going backward in time to figure out what is the value at every time t less than t star. Okay? All right. So let me just do the derivation of characteristics. It's very, very, very simple. Okay, don't worry about it, because whatever follows is much harder than that. But here is this thing. So remember, x dot equals to f of x theta. There's no t dependence here, so we are fine. Okay? So by x of t, I mean I start at some x t equals to 0. I solve the ODE, and I get x at t equals to t star. Okay? This is what I mean by x of t. It's a trajectory starting from initial condition to final condition. Okay. Now I want the adjoint on this trajectory. So v of xt at time t. Okay. So what I want here is do the total derivative d by dt of this. So if you do the total derivative of this, you will get what? What is that? dv by dx, right? That's the total derivative. Okay, but dv by dx is grad v. dx by dt is f. Right? And this is 0. This is my L dagger. So on trajectories, my adjoint is constant, because all it does is it takes information. So I know what v of x at t star is. That is just g of x. So it should be g of x here. Also, it should be g of x at any time. And that's how I do it. So I don't have to solve the PDE. All I have to do is solve my ODE. And at every trajectory of the ODE, I know what the adjoint solution is. Okay. I'll erase this later, but for the sake of this theorem, let's continue. Yeah. All right. Okay. So this is constant characteristics. That means on trajectories, it's 0, which means that when you evolve, you get the same value. Okay. So now we know SI is theta, we know the quantity of interest is this, so the g function is just x. So g of x is just x1, okay? And I plug all of that inside there, I compute the integral, I get the sensitivities, okay? We will have to derive how we get that, and the derivation comes from, okay, again, another question. How many of you have taken linear algebra where you have worked with adjoints? No. Never, okay, okay. So does this equation strike anything to you in terms of linear algebra? So this is the inner product of x and a matrix times another vector y. And in inner products, you can move this matrix to this side, but when you move it, you transpose it. Or in a very formal setting, when you move it, you apply the adjoint of that thing. That transpose in real field is called is the adjoint, but in a general inner product and general field, it's just the adjoint. Okay? So when you move it there, you do this. Now, what von Neumann did was you can do the same thing with differential operator. If you move a differential operator there, you apply the adjoint. But now, because it's not linear algebra, it's a differential operator, you'll have some boundary terms. Okay? So that is what this is. So what does it mean to have an inner product for ourselves? This is the inner product. It takes a function, it takes an L times V, and just integrates them in space and time. Because in inner product, you have to get a scalar, right? So if you just integrate the differential operator in space and time, you get a scalar. Okay? Now, just move L to here and figure out what that L looks like. And that is the adjoint. So if you want to move L from right to left, you have to do integration by parts. So that is the whole thing. So which means that take the derivative in W, transfer it to V. So when you do integration by parts, you get boundary terms. So that is exactly what you get. If you follow this thing, you will get, now all the derivative information is in V, so this must be the adjoint. And this was exactly what it was, d by dt plus grad times V, right? Okay, so that is the adjoint of that differential operator. This is our Liouville operator that described the evolution of probabilities. This is the adjoint operator. All right. The next step, and I'll be quick here, is if we want to find out the sensitivity with respect to some parameter Si, we need to find out the evolution equation for d rho by dsi, or d probability by dsi. Now this is very tricky because the probability is time varying. It's not explicitly dependent on S, on the parameter. Remember, the parameter was of the model, right? There is an initial condition, and so time varying densities had the dependence. So you cannot just do this standardly. So you have to apply this, you have to figure out how does Si evolve in time, this capital Si. So I ran out of alphabets, so I'm using small letters Si and big letters Si. But the idea is apply this to the operator, collect all the things that you know, and now you know that this is 0, so the dsi, this is the evolution equation for the sensitivity. Okay.
Small s represents a parameter.
Yeah, yes. So like for example, theta, it could be theta, or it could be the parameter of the initial condition. For example, mean or covariance.
Of the initial state.
Of the initial state, yeah. Of the PDF describing the initial state, yes. So you do this, you get the evolution equation. Okay, now comes the step 3, which is the hard part. But the idea is you add 0, you make a function of 2 variables by adding 0, and then you take derivatives, and then you figure out, oh man, they have to match somehow, so that must be the equation of the adjoint. So what do I mean by 0? You want the derivative of the quantity of interest, right? So you put that on the left-hand side. This is 0, because L of the P is 0, right? It's the Liouville equation. So this is 0, so you've added 0. So it's fine. Now take the derivatives with respect to the parameter. And once you take derivatives with respect to parameters, you know what to do. You take the L and put it in V, right? So you do the adjoint thing here. So once you get to the adjoint thing, you now collect all the things that you have and make things 0. So in order for things to cancel out, this LV minus V divergence F has to be 0. That's what you get for the adjoint equation. So you can go through this derivation, and I can point you out to the paper, but the idea is just follow all the things and make things 0. And that is what you get. Okay. Oh, yeah, there's some more things, but All right. So yeah, I can stop here now before I go to the next section. Uh, but yes, so the idea with adjoints is you always want to figure out what the adjoint operator is for the differential operator that you have. Once you have that, you can use it to find out sensitivity evolution of any parameter with respect to any parameter. And it's just by following this thing blindly. Once you have the adjoint differential operator, just do this blindly. What I will show you is that we can also use this to figure out an error estimate, which is very useful for computational sciences purposes. But yeah, sorry, this is a little bit more mathematical than it should be, but the idea is this is fairly new things, and I want you to see what operator theory and adjoints are before you read any of the paper. Okay, so the next section, what I will do is I will talk about, I just told you that in order to find the exact derivative, you need to know the time varying probability density. Well, that is the thing that you don't know. So how will you find out the derivative, right? If you knew the time varying probability density, then you have solved the problem. So all you know is the initial probability density, and that's it. So here we use AI. And what we did was we tweaked normalizing flows, and I'll talk about that. And we added time into the normalizing flow, and the normalizing flow learns how densities evolve over time. So I'll talk about that. This is, and I'll give you two examples of where we solved AI for very two simple examples, and tell you how we computed the sensitivities of those. Yeah, so we can probably meet around 3-ish, and then. Okay, all right. So in order to learn the sensitivities, we have to solve this equation. The V, as I said, is coming from the adjoints, so that's not a problem. But the problem here is we need to know what the probability density is at space-time. And that is a problem because all we know is the initial probability density, right? So we don't know the full time varying probability density. We can technically get it by solving the Liouville's equation, but as I said, we cannot solve it. It's high-dimensional PDE. So what do we do? The idea is we try to mimic it. And all right, so the idea is try to mimic this probability density with AI. And what do I mean by that? So our problem is that this time varying probability density is coming as a solution of this Liouville PDE, but I need that to compute the sensitivity. Okay. So what if I make this P of xt a neural network? So the only thing I know to give to the neural network is the initial density, right? So how do I train it for each other time? And we do it in a way that is kind of hacking the normalizing flow. And what I mean by hacking the normalizing flow, well, what does normalizing flow does? So suppose you have a data that is coming from a distribution that you don't know, okay? And all you know is a simple distribution, let's say the Gaussian distribution. So you can take samples from the Gaussian distribution, or you can evaluate the likelihood of the Gaussian distribution at certain points, right? So, and you don't know what your true data density is coming from. So how do you learn the density of that? Well, before normalizing flow, how would you do this, right? So this would be what, when you do a Python thing, you give it data, it will do the KDE estimation. And KDE is a kernel density estimate, it's actually estimating the PDF. So what it is doing is it's binning the data and using kernel functions on the bins and figuring out the probability density function of your data. That only works in 1 or 2 dimensions. Right? So in higher dimensions, how do you do density estimator? And for a long time, it was a big problem. I mean, there are versions of KDE that have now been extended to higher dimensions, but high dimension density estimator were a big problem until normalizing flows came to the picture. And the idea of normalizing flows is very simple. It lies in change of variables. And what it means is that if I have a random variable that is coming from a probability density function, if I apply a transformation to it, then I get another probability density function, and those two probability density functions are related by the change of variables. Okay? So can I use this thing to figure out what my data distribution is? What should be the transformation such that it coincides with the data that I have? And that is the idea of normalizing flow. Okay? So here, what I've shown is one normalizing flow that takes a simple normal distribution and maps it to this complicated looking data distribution. And the idea is such that this distribution should correspond to your data. So your data should be samples from this distribution. That is the whole idea. So how do you know that your density is the right density for your data? Well, we have maximum likelihood estimator, right? So somehow you have to figure out a mapping such that it maximizes the likelihood of the data, right?
But then you have the overfitting issues.
You do have overfitting issues. So surprisingly, if you have enough data and it had in medium dimensions, those overfitting issues kind of tend to go away. But yeah, you do have overfitting. In fact, how to regularize normalizing flow has always been a problem. What I will show here is that you can regularize it for our problem using that pin losses. But that is a good point, yes. So if you have enough data, you can do this. If you don't have enough data, you definitely will overfit. And then there are all these hyperparameter stuff that you have to do to figure out. Yes. And there are other issues with normalizing flows also. So the way the normalizing flow works is in the transformation in the same space. So by that what I mean is that if your data is in some d-dimensional space, your transformation is also in the d-dimensional space because it works with change of variables, which requires invertible diffeomorphic transformations. Now, if you have a very high dimensional space, you cannot naively use normalizing flow because then you will be restricted to a flow in the same dimensions. So to alleviate that, they came up with the variational normalizing flow. The idea is you work on the latent space, you do your transformation in the latent space such that it maps to some density in the high dimensional space. But the whole flow is in the same dimensions. Okay. All right. So I said maximize the likelihood, which is same as minimize the negative log likelihood, right? All right. And on the top, I have your input x. When it flows through some transformation, you get your z, right? And then with your z, you should be able to apply the inverse function so you can get x. And so why do we need the inverse? That's where if you look carefully at the change of variables, you will see that suppose if y is g of z and you know the probability density of z, then the PDF of y is given by the change of variables here. And in here you need the f is the inverse function of g. So the change of variables involves two things. It involves the determinant and the inverse function of the transformation. So why is this important? Because if you learn the flow from Gaussian distribution to your data space, you also need to learn the inverse simultaneously. So every normalizing flow has to do both. Okay, so it has to learn both. So that's why all the transformations are kept simple. So for example, diagonal transformations are invertible. It's very easy to invert them. Or you do lower triangular matrix or something like that in which you actually know the inverse. And if you compose a lot of these things, the determinant gets multiplied, so it's easy. So that's why this is not a problem. But estimating the determinant is always a problem for a function. So that's why you have to keep those functions very simple. Again, if it's a lower triangular, then it's just a product of the diagonal entries.
So it's like you keep the condition number as low as possible.
Yes, exactly. So you have to make sure that the transformations are very simple. The non-linearities that you add, you have to be careful with them. So that's why the ones that work are very simple. The affine coupling, the neurospline. So those are the transformations that work. Okay, but if you have noticed one thing, this won't work for us because there is no time here. So all this is doing is that, if you have an initial PDF, if this is your initial PDF, it's learning a transformation from Gaussian to initial PDF. That's about it. So how do we include time in here? Well, that is what the novelty of this paper is. Although we're not the first one, apparently we discovered that we didn't We didn't invent temporal normalizing flow. So when we wrote this paper, there was already somebody who had written the paper, and it was sad, but we use the same ideas for a different problem. So the idea is, if you have a base density, which is standard Gaussian, you transform it to t equals to 0. You use the same density, you transform it to t equals to 1. So in this transformation, you use time as a parameter. And you have to make sure that the way you treat the parameter in time, it indeed is a density over space-time. That's the only thing that you have to worry about, which means that don't worry about time much. So you pass the time to the neural network, but you inside it, you take the time away, you do all the space manipulation, you kick back the time in, and then you get the density estimator. So it's slightly tricky, but all you have to do is make every layer in the normalizing flow dependent on time somehow, right? And it should do just a simple thing with time, just multiply a times t, that's it, things like that. All right, so if you do that, you can do this. But again, how do we fit this p of xt? So remember what I told you about. How do you fit a normalizing flow? You minimize the log likelihood, which means you must have data coming from the true density. You don't have data coming from the true density. Well, you can push forward the initial density through your ODE, right? So you have the initial density, you have your ODE. When you evolve it to the next time step, you have data from the time density. So you can do KL divergence, and that's called the forward KL divergence. And that's not the only thing. You actually can do the reverse KL divergence here. And I'll show you how we do this. Actually, this is an important theoretical thing, but practically it requires derivatives with respect to your ODE, which is adjoints in the ODE space, which is hard. It's expensive. Okay, but the top one, the forward KL, is just maximizing log likelihood. So it's easy, but it has problems. Okay, so how do you do the forward KL? The forward KL is you get samples from initial density, you again you propagate them through your ODE model, and you do the log likelihood. Because maximizing the likelihood is the same as minimizing the forward KL. Those two are same. Okay. Now, whenever you have a neural network, you have a loss function. So you have to evaluate the loss function. You have to take derivatives with respect to the loss function. With the forward KL, taking derivatives with the loss function is very easy. It's not that hard. With the reverse KL now, the expectation is with respect to your learned estimator. Okay. Then it becomes a problem because the P, you no longer need samples from the true P, you need to evaluate the likelihood using the 2P. And that is a problem. Let me tell you why. So this is the reverse scale expected with respect to P hat. So you cannot compute this expectation because you have to take samples from your P hat and evaluate them at P. That's a different thing, right? So how do you evaluate P of xt? You cannot evaluate P of xt. You can estimate samples from probability at xt by transporting initial density, but you cannot evaluate the density, right? Because you don't know the density. Yes. So there is a trick here, and we were very happy when we discovered the trick using backward characteristics, but apparently someone also did this in the neural ODE paper. They called it differently. They were not looking at doing this, but it's the same form. So what we do is, this is your normalizing flow density. You know it's a transformation from a base density. So you can do change of variables. So you can transform that to change of variables with respect to base density. And now this is this thing. This is easy to evaluate because this is the normalizing flow. So you can evaluate likelihood in normalizing flow. This is your normalizing flow H. So that's not a problem. This is what you have to evaluate, right? So how do you evaluate likelihood when you don't know the form of the true density? That comes from characteristics again. So what I want you to focus is from the bottom to the top, right? So what does the bottom mean? It means that this is your initial PDF. Okay? You know the PDF at every point. Now this is your PDF that you want at t. Suppose I take a point here and tell you what is the likelihood of P of xt. You don't know that, right? So what do? Take this x, evolve it backward using your ODE to the point it came from the initial condition. Right? Because ODE are one-to-one from initial condition to the state. So when you evolve it backwards, you will get the initial condition. You know its probability likelihood. You clump this together, and this is the characteristics equation of likelihood. It tells you how likelihood evolves. So if you solve this ODE together, you will get the likelihood of this point back here at P of xt. So you can, in principle, compute likelihoods of points even if you don't know the true density. We thought this was enough to solve the problem, but remember the sensitivity depends not only the likelihood values, but the derivative and divergence stuff. This you won't get. You have to do some finite difference. And in high dimension, finite difference is bad. Right? Okay, so, but we can use this for getting likelihood, and we can use this to compute reverse scale. The problem with reverse scale is when we take derivative with respect to loss function, we now need, because we are doing a backward evolve, we now need a derivative of how the ODE changes when you change this. So if x is a little bit here, you will get some little bit difference here. What is that derivative? You have to do automatic differentiation or add joints of the ODE to figure that out. That is hard. Okay. All right. And what other problems do we see when we backward evolve? So whenever ODEs get stuck in some state, if you want to backward evolve, it's very numerically unstable. And I'll show you an example where ODEs get stuck in states. Okay. All right. So once you have a loss function, you have trained your normalizing flow. You can now use the normalizing flow to estimate the quantity of interest, right? Now you can just plug in the normalizing flow, and this is your estimator. We also found out that you can do the error. So this is the true quantity of interest minus the estimated quantity of interest. That also depends on the adjoint. Okay. So this is a surprising result because this gives you the error of the quantity of interest without knowing the true density and a computable error estimate. This is very big because everything here is in terms of estimator and the initial density you know. So you can compute this error without knowing the true density. And that is, I think that I was very happy with this. This is our main paper. Like this leads to our main result. So in every result on neural networks, whenever you do generalization error and stuff like that, you need to know something about the truth. Here we are telling you don't need anything to know about the truth. You will get an error. And that is we feel is important. Yes. Yeah, you don't need it. It's just computable. Of course, to compute this integral, you will have to use some Monte Carlo. But again, you can turn this into a Monte Carlo with respect to p hat. So everything is computable here. This is our huge thing. Of course, the proof I'll give you quickly. Okay, sorry. This is the estimated q hat. This is the true q hat. You don't know this. So error is just difference between the expectation. Expectation is linear, so it goes inside. Let's call this the error in the probability density, P. Okay. Now, what did I tell you about adjoints? Is that if you want to compute something in an integral, you pass the adjoint operator in there. So what it means is that if I take the inner product with the error in P with my adjoint solution, I can transfer the adjoint to the error in here and get a boundary term. Now this is linear operator. So this is P and P hat. This goes away because this is the true density. So now you can compute this, you can compute that, and this is your error. Okay? So that is the whole idea. Which is written in words here. If you do the thing integration by parts and do the thing over here, you get the error estimate. So this is the error estimate. Okay. What will I'll do next is basically our loss function is now the integral of the loss function. And remember, this was the KL divergence at each time. So you just integrate over time. Okay. Now, what we found out was if we do this, our estimator was very bad at initial time and would get better at later times. This is because of the regularization problem, that KL divergence doesn't have a true regularization. So it can give you wonky results. For us, we found out surprisingly no idea why that initial density was always getting underestimated or overestimated. So what we did was we added a pin loss, which means that we take some space-time points and ask our estimator to satisfy the Liouville equation for the space-time points, which is d p hat by dt plus. Because this is p hat, we can compute that everything, and then we say that, okay, regularize it now. KL is not symmetric, but if you add the reverse KL, then it is symmetric if you do half weights. Yeah. But we didn't add the reverse scale. I mean, that's only for theory purposes because it was hard to do practically. But we did regularize it with pin loss. Okay. So now I'll show the two examples and that'll be the end. So let's see. So we have a model parameter which is 3. We are interested at time t equals to 1 of these quantities of interest, which is what is the probability that the state is in some rectangle, what is the first moment, what is the cross moment. I mean, these are all second order moments, right? So these are the quantity of interest and we want its sensitivity and the error that we get without knowing the true density. And this is for the linear dynamical system, this one that I showed you. We know everything. We know what the true result is. And this is a rectangle that we care about. So at every time the rectangle is fixed, as the state evolves, it either goes inside the rectangle or not. So you know the probability that it will stay in the rectangle. Okay. But the important thing is this is not in terms of a moment. So your moment estimation methods will not be able to compute sensitivities with respect to that. Okay. But we did it for using our normalizing flow, and these are the results we get. So the dq by d theta are almost exact. If you do this, they're almost exact here. This is the true ones. And the error in quantity of interest are in the order of -3. Okay. So with just 10 points in time, we were able to learn the temporal normalizing flow. I mean, you could argue this is a linear one. But the hard point here is that a fat density is becoming very elongated and stretched, even for a linear dynamical system. So it's very, very tricky to do sensitivities.
So if the correlation is increasing.
Yes, in this direction, yeah. But again, as you see, this is nonlinearly in terms of parameter. So.
But when the correlation increases, then what does the sensitivity mean then? Because then the parameters are so much correlated, then can we comment on individual sensitivities?
Well, sensitivity is with respect to model parameter, right? So it could happen that the second moment, so here you see, right? What does it mean sensitivity with respect to parameter? So if theta is large, this is going squarely with the parameter.
Okay.
The second moment. Whereas this one doesn't even depend on the parameter, the x1.
Yeah, the first one.
Yeah. So we want to be able to estimate that, right? That is an important thing. Okay, but the whole point to show you is that if you plug this in, you will figure out that they are exact almost. Like there's no even, and I don't have how I turn them into Monte Carlo impedance sampling because that's another problem. Okay, now for something difficult. So here I take a nonlinear ODE. Okay, not only is it nonlinear, it's a double attractor, which means that you see this initial condition, there are two attractors here in the dynamical system. As the dynamical system evolves, the state is either getting pulled here or pulled here. So it becomes two direct deltas as time goes on, right? So you can think of this as magnet. An initial condition is pulled. If it's on the left of 0, it gets pulled here. If it's on the right of 0, it gets pulled here, okay? So very difficult bimodal behavior, and we are interested in these two quantities of interest. Okay. Now, we also have parameters that are the mean of this initial distribution. So we are asking how sensitive, if my initial condition was here, almost 90% of the mass will get pulled here. So we are very interested in the sensitivity. And the cool thing about what we are doing here is that the framework doesn't change. You change nothing. You don't change at all. You solve that same Q with respect to SI. Okay? So let me show you how our TNF learns this density. So you can see it getting stretched to the two bimodal distribution as time evolves. So that is a very bimodal distribution. Learning that in time is as hard as it gets, but we are able to do it with a KL divergence and a regularizer. That is very, very amazing. But not only that, now we get the sensitivity vectors. So we get dq1 by, we get the whole gradient. Okay. Sorry?
We get all the moments.
Yeah, we can also get the moments. Yeah, yeah. But yeah, we get sensitivity with respect to the two parameters here, which are initial condition within the same framework. So we don't have to change anything. And all of this can be done parallelly. So each quantity of interest and each parameter can be run completely parallel. There's no dependence on that. Yeah, and all you have to do is take the same initial samples for each batch.
And theta could be a vector, right?
Yes, theta could be a vector. So here I just had one,
Yes.
but it could have multiple things here, right?
Yeah, but then is there also a way to understand the correlation between these parameters?
When you say correlation, so I haven't taken the parameters as a random variable, right? They're just some values. So it's a gradient at that point.
Okay.
You could think of that as correlation, but then you have to evolve the density in the space, in the state and the parameter space.
Okay. So generally then, like, does change in theta 1 affect change in theta 2, something like this?
Yes, that you cannot do it.
Okay.
With local sensitivity, you cannot.
Okay.
So local sensitivity is only giving you derivative information locally.
Yeah, okay.
Now to get global information from local derivative information, that's manifold theory. You have to use some sort of manifold theory to do that. But then you have to get, you have to explore the parameter space and you have to get these local derivatives everywhere and then compare them. That's the best way to do it. If you are thinking of doing it globally, like Sobol, then that's a way, but I don't know how you will do it with Sobol here. So, but yeah. So these are local sensitivity, and I think that's it. I will not talk about the inverse one. I think we'll finish it here. But the idea, the second slide, potential second slide, was going to be the inverse problem of this. So basically, instead of propagating a forward density through a model, suppose now you want to infer the prior, or you want to get the posterior given the prior. And the way you do is you can turn this Liouville equation into a sampling method and get samples from the posterior. And yeah, the Liouville equation is a surprisingly sneaky equation that comes around in uncertainty quantification. So yeah, I'll stop here.